Hi sir, good evening sir. Myself Sugnakar Rao. I am from CSC department and my roll number is 244 and my topic is about de Broglie's hypothesis. An introduction to de Broglie's hypothesis. De Broglie's hypothesis proposed by Louis de Broglie in 1924 revolutionized the understanding of matter and waves. It suggests that all matters has wave-like properties, a concept that links quantum mechanics and classical physics. This hypothesis is paved the way for the development of wave-particle duality, a fundamental principle in quantum mechanics. And there is verification of de Broglie's wave hypothesis by the diffraction from graphite. And next is background of Louis de Broglie. Louis de Broglie was a French physicist born in 1892, known for his groundbreaking work in quantum theory. He was awarded the Nobel Prize in Physics in 1929 for his contribution to understanding a wave-particle duality. De Broglie's idea was influenced by earlier in physics, particularly that of Einstein and Planck, and its side of the image of Louis de Broglie. Wave particle duality. Wave particle duality is the concept that particles such as electron exhibit property of both wave and particle nature. This duality is fundamental to quantum mechanics and challenges classical physics views of particles as well define entities. De Broglie's hypothesis introduced this duality for all matters, not just like expanding the scope of quantum theory. He writes that the duality of a particle looks like here wave and particle properties. The wave-like and particle-like wave properties are shown in the graphic model. The de Broglie's wavelength. De Broglie introduced the concept of wavelength associated with a particle given by the formula lambda equal to h by p, where lambda equal to wavelength and h equal to Planck's constant, p equal to momentum of the particle. This relation allows for the calculation of the wavelength of any moving particle, reinforcing the wave aspect of matter. Next, P is equal to mv, mass into velocity. De Broglie implications for electrons. De Broglie's hypothesis particularly applies to electrons, suggesting they can behave like wave under certain conditions. The wave nature of electrons leads to phenomena such as electrons diffraction and interference pattern. This wave behavior is critical in understanding atomic structure and the behavior of electrons in atom. Experimental condition. The de Broglie's ideas was experimentally confirmed by Davison's German experiment in 1927. In this experiment, electrons were diffracted a crystal demonstrating their wave-like properties. The result aligned with de Broglie's prediction, providing strong support for wave particles duality. Here using diffraction equation, where diffraction equation is d sin theta equal to n lambda, sin theta equal to n lambda by d equal to 1 into x. Quantum mechanics and de Broglie's theory. De Broglie's hypothesis lays the groundwork for the development of quantum mechanics in the early 20th century. His ideas influenced in key figures like Schrödinger's, who formulated wave mechanics based on de Broglie's wavelength concept. The connection between wave functions and particle behavior is cornerstone of some modern quantum physics. Applications of de Broglie's hypothesis. De Broglie's hypothesis has application in various fields including computing and nanotechnology. Technologies like electrons microscope utilize the wave nature of electrons for high resolution imaging. Understanding wave particles duality is crucial in developing new materials and quantum devices. And challenges and limitations. While revolutionary, de Broglie's hypothesis does face challenges in explaining all quantum phenomena. The concept primarily applies to microscopic particles and does not readily extend to macroscopic objects. The interpretation of wave particles duality continues to be a topic of debate and research in quantum theory. And we observe that verification of de Broglie's hypothesis was done and the School of Science Engineering, Azumeria Shahins and Muhammad Sabira Anwar's LUMS School of Science and Engineering. The answer depends on how we choose to look at it. Some of outcomes are explained with the particle photon model and some with the wave model. For example, light that is capable of knowing out electrons from a metal can also diffract aspect. We now accept the truth nature of light cannot be described by a single picture and that both the models complement each other. After the great success of dual particle wave nature of light, de Broglie postulated that photons exhibit both the wave and particle characteristics. Perhaps all forms of matter must obey the same wave particle duality. The current experiment is designed to verify de Broglie's hypothesis diffraction of electrons from polycrystalline graphite. The main emphasis is on image processing using digital photography, and ultimate students will be able to determine the interplanar spacing of the graphic crystal. Keywords: de Broglie's relation, Bragg's law, electron diffraction, fluorescent materials, thermonic emission, crystal structure. Conceptual object. In this experiment, we will learn about the wave-particle duality of matter in particular electrons, understand and verify de Broglie's relation, get familiar with Bragg's law and learn about its implication. Learn about the functional principle of electrons tubes. And last conclusion is about conclusion and legacy. Conclusion is de Broglie's hypothesis remains is a fundamental concept in modern physics, influencing both theory and experiment. It illustrates the interrelation between matter and waves, reshaping our understanding of the universe. The legacy of de Broglie's work continues to inspire physicists and researchers in the quest for knowledge in quantum mechanics. Thank you, sir. Thank you for giving this opportunity to me. Thanks a lot.